Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says.
So imagine we could take the very CO2 that's warming our planet and turn it into something incredibly useful, like the building blocks for plastics, fuels, or even medicines.
Not just imagine, but actually do it. And do it with such precision that we're essentially using an atomic scalpel to perform the chemical transformation. That's the groundbreaking idea behind a new development from researchers at ETH Zurich.
An atomic scalpel for CO2? That sounds like something out of science fiction. Are we talking about some kind of sci-fi device, or is this a tangible chemical breakthrough?
This is very much a tangible chemical breakthrough. These researchers, led by Professor Javier Perez Ramirez, have engineered what they call a single-atom catalyst. Essentially, individual atoms of a metal, indium in this case, isolated and anchored on a support material. And it converts CO2 into methanol with an unprecedented level of efficiency. It's a leap forward in thinking about how we design these chemical processes.
Wow, so not just converting CO2, but doing it with such surgical precision at the atomic level that is radically more efficient. That immediately begs the question, why is converting CO2 to methanol such a big deal, and why have we struggled with it until now?
That's the crux of it. When we talk about CO2, we're really grappling with a twofold challenge. On one hand, it's the primary greenhouse gas driving climate change. On the other, the global chemical industry is fundamentally built on fossil fuels, both as an energy source and as the raw material for countless products. We have this linear, unsustainable model of extract, use, release CO2.
And CO2 capture and utilization, or CCU, is supposed to break that cycle, right? To turn CO2 from a problem into a valuable resource.
Exactly. CCU aims to pivot us towards a circular carbon economy. Instead of just burying captured CO2, we want to give it a second life. And among the many things you can make from CO2, methanol stands out. It's been called the Swiss Army knife of green chemistry because it's a foundational chemical for so many things: plastics, paints, solvents, even as a clean-burning fuel. It's a way to close that carbon loop.
So the reaction is CO2 plus hydrogen equals methanol and water. Sounds simple enough on paper. Where's the struggle part you mentioned? What's the energy hurdle?
Well, CO2 is an incredibly stable molecule. It's low energy, which is great for its persistence in the atmosphere, but terrible if you want to activate it and force it to react. To get it to combine with hydrogen and form methanol, you need a substantial energy input. Traditionally, this process has required really harsh conditions. We're talking temperatures above 240, 250 degrees Celsius and pressures up to 50 to 100 times normal atmospheric pressure.
That's a lot of energy. And if that energy comes from burning more fossil fuels, you're just moving the problem around.
Precisely. That's where catalysts come in. A catalyst's job is to lower that energy barrier, to make the reaction happen more easily at lower temperatures and pressures without being consumed itself. For decades, we've relied on catalysts to make this process even remotely viable, but they've always had their own set of limitations.
And that brings us to what these traditional catalysts actually look like and why they might not be as efficient as we need them to be.
Not at all. For a long time, the industrial standard has been what we call heterogeneous catalysts. Think of them as tiny metal nanoparticles, little clumps of metal dispersed on a support material. For methanol synthesis, common ones involve copper, zinc oxide, or indium-based compounds. The crucial thing is that the chemical reaction only happens on the surface of these metal nanoparticles.
So a nanoparticle is essentially a tiny sphere of metal, right?
Exactly. And the problem is, a significant fraction of the metal atoms in that sphere, that clump, are buried in the interior. They're not exposed to the reactants, so they're completely inert. They're just taking up space. This is a massive inefficiency, particularly when you're using rare or expensive precious metals like platinum or palladium. You're paying for atoms that aren't actually doing any work. The atom utilization efficiency can be astonishingly low. Sometimes less than 10% of the atoms are actually active.
Less than 10%? So for every 10 atoms you put in, 9 are essentially ballast? That's a huge waste of resources.
It really is. It's like having a factory where 90% of your workers are standing in the break room, not on the assembly line. And this is where the single atom catalyst, or SAC paradigm, really shifts things. Instead of those clumps, imagine isolating every single metal atom and anchoring it individually across the surface of your support material.
Ah, like spreading out all your workers so every single one is at a workstation.
A perfect analogy. In a SAC, every single metal atom is a potential active site. This pushes atom utilization efficiency towards 100%. You're getting the absolute maximum bang for your buck from every precious atom. But it's not just about efficiency. These isolated atoms behave differently. They have unique electronic and geometric properties because they're not bonded to other metal atoms in a bulk structure. They're strongly interacting with the support material, which can fundamentally change how they bind to reactants.
So they're not just more efficient because more atoms are exposed, they might actually be better at the job themselves?
Precisely. And this leads to another huge advantage: well-defined active sites. With nanoparticles, you have atoms on corners, edges, faces, all behaving slightly differently. It's a chaotic mix. With SACs, every active site is uniform. It's one isolated atom, so the system is much more homogeneous and predictable. This was a concept first formally introduced around 2011, and the field has exploded since then.
Okay, so the concept of SACs is a game changer. But the ETH Zurich team applied this to CO2 conversion using indium. Indium isn't a precious metal like platinum, so what's the big deal with their specific innovation?
That's a great question, and it highlights a key insight from their work. Indium has actually been used in catalysis for CO2 to methanol for over a decade, but always in the nanoparticle form, those clumps we talked about. The ETH Zurich's breakthrough was finding a way to isolate individual indium atoms and anchor them onto a hafnium oxide support.
Hafnium oxide? That's not a common household name. Why that particular support?
The source material doesn't go into deep specifics about the choice of hafnium oxide, other than describing it as providing a stable surface. But the critical point is that these isolated indium atoms, even though indium isn't as rare or expensive as platinum, are significantly more efficient at catalyzing the CO2 to methanol reaction than indium in its traditional nanoparticle form. This demonstrates that the single atom approach isn't just for super expensive metals. It can unlock superior performance even with more common elements.
So they've taken an existing catalytic element, indium, and made it perform much better by turning it into a single atom catalyst. How much better are we talking, and how does this atomic level precision translate into real-world efficiency gains?
The reports indicate a substantial improvement. The single atom catalyst led to a significant increase in methanol production efficiency compared to traditional methods. That's a massive leap.
That's not incremental, that's transformative. What's happening at the atomic level that allows for such a jump?
The researchers posit it's a combination of factors. The stable surface of that hafnium oxide support plays a role, but critically, it's the unique and flexible chemical potential of the isolated indium atoms themselves. They interact differently with the reactants. There's a synergistic effect that enhances how CO2 is activated and then how it hydrogenates to form methanol. Essentially, the reaction can proceed much more readily, leading to higher yields under less extreme conditions.
And how do they manage to keep these individual indium atoms from clumping together? Because at the high temperatures typically involved in these reactions, atoms usually want to get together, right?
You've hit on one of the most critical challenges in SAC development: stability. Atoms naturally tend to migrate and agglomerate into more stable nanoparticles, especially at high temperatures. If that happens, you lose all the unique benefits of the single atom configuration.
So how do they freeze them in place?
The ETH Zurich team used a sophisticated fabrication technique. This technique effectively freezes the individual indium atoms, embedding them stably on the surface of the hafnium oxide. It's a bit like flash freezing something so quickly that its structure is preserved at an atomic level. This robust anchoring is key for the catalyst's durability in a real-world reactor.
That's a really clever engineering solution. So, by maximizing active sites, using this sophisticated fabrication technique, and harnessing the unique properties of isolated indium atoms, they've not only made the process more efficient, but also more resource and energy efficient.
Exactly. Resource efficient because you need dramatically less indium to achieve the same or better catalytic activity. Even though indium isn't platinum, it's still a finite resource, and using it judiciously is a core principle of green chemistry. And energy efficient because if the reaction proceeds more easily, you don't need those extreme temperatures and pressures, which means significant energy savings and a smaller carbon footprint for the whole methanol production process. Professor Perez Ramirez himself emphasized that their study shows isolated indium atoms allow for more efficient CO2-based methanol synthesis than the nanoparticle forms.
This all sounds incredibly impactful from an engineering and production standpoint, but the source material also talks about a clearer window into the fundamental mechanics of catalysis. What does that mean? How does moving to single atoms give us a better understanding of the science itself?
This is arguably one of the most profound impacts of single-atom catalysts, and it moves beyond just making a better catalyst. Historically, catalyst development has often been described as a trial-and-error process, almost an art form. Researchers would mix different materials, test them, tweak them, and iterate, kind of a throw it at the wall and see what sticks. In many ways, yes, because traditional nanoparticle catalysts are such a black box. The surface of a nanoparticle is incredibly complex. You have atoms on flat faces, sharp edges, corners, all behaving slightly differently. It's incredibly difficult to pinpoint which specific atomic arrangement is the most active site, or exactly how a reaction is progressing at the atomic scale. Reactants go in, products come out, but the precise atomic level mechanisms remain largely obscured.
So with a single atom catalyst, because every active site is identical, it's like lifting the lid off that black box.
Precisely. The system becomes uniform and well-defined. This homogeneity provides an unprecedented opportunity to study the reaction mechanism with high precision. Scientists can now observe with much greater clarity how reactant molecules like CO2 and hydrogen interact with a specific, known active site, that single indium atom. This allows for a more systematic and rational approach to catalyst design, transforming it from a trial-and-error art into a predictive science.
That's a huge shift. So instead of just seeing the overall effect, they can actually watch the reactions step by step.
In a sense, yes. Researchers can use advanced techniques, which allows them to observe the catalyst at work under real reaction conditions. They can identify the transient molecular species that form on those indium atoms as CO2 is converted to methanol. This level of detail is almost impossible with the complexity of nanoparticle surfaces. It's like going from a blurry, distant photograph to a high-resolution, close-up video of the exact atomic dance that's happening.
So it's not just that they built a better mousetrap, they've also built a better way to understand mousetraps, which will help build even better ones in the future.
Exactly. This ability to directly probe the structure-function relationship, how the specific atomic arrangement dictates catalytic performance, is a monumental leap. It allows scientists to answer fundamental questions about why a catalyst works the way it does, not just that it works. As one report put it, it gives them a clearer view of the chemical processes happening on its surface.
And the implications of this methodological leap you mentioned extend beyond just making methanol.
Absolutely. The principles demonstrated by the ETH Zurich team provide a powerful blueprint for the future of catalyst development across a vast range of chemical transformations. Once you understand the fundamental reaction mechanisms at the atomic level, you can start to design new catalysts with intention. You can computationally predict which combinations of single atoms and support materials will be most effective for a specific reaction.
So if they find a bottleneck in a reaction, they can design an atom specifically to overcome that bottleneck.
That's the dream, and it's becoming a reality. If a particular reaction step is identified as the rate-limiting bottleneck, researchers can now design a catalyst specifically to lower the energy barrier for that exact step. This kind of precision engineering could dramatically accelerate the discovery of new catalysts for other critical sustainable processes.
That's incredibly powerful. It sounds like this atomic scalpel approach is not just about making a single process more efficient, but about fundamentally changing how we approach chemistry for a sustainable future.
It truly is. It transforms the catalyst from a static material into a dynamic, designable tool. It provides the foundation for what Professor Perez Ramirez and his colleagues hope will be a fossil-free chemical industry, driven by catalysts designed with atomic-level intelligence. It's a shift from trial and error to rational design at the most fundamental level.
This is genuinely fascinating. So, to recap the key insights from this groundbreaking work, first, the shift to single-atom catalysts is a game changer for efficiency.
Absolutely. By ensuring nearly every metal atom is an active participant, you dramatically reduce waste, lower costs, and make much better use of finite resources, pushing atom utilization towards 100%.
And second, this precision engineering isn't just about better performance, it's about better science.
That's right. Moving beyond the black box of traditional catalysts, single-atom catalysts provide uniform, well-defined active sites. This allows researchers to deeply understand fundamental reaction mechanisms, transforming catalyst development into a more predictive and rational scientific discipline.
And finally, what this means for the broader picture of sustainable chemistry.
This breakthrough makes sustainable chemistry far more viable. It significantly lowers the energy needed to convert CO2 into methanol, a critical building block. It's a tangible, impactful step toward a circular carbon economy, where atmospheric CO2 can truly be seen and utilized as a valuable raw material for a more sustainable industrial future.
It really makes you think about how much hidden potential there is in seemingly inert molecules like CO2 if we just apply enough ingenuity and precision. What other chemical transformations are currently locked behind an energy barrier that could be unlocked by this single-atom approach?
Keep reading the fine print.